Hello. So we are going to go over an application of Newton's third law, which is internal forces or pulley systems. So let's get started. So the first part of this sheet is just looking at some quick applications of Newton's third law, just identifying the two pieces of a force where A acts on B and B acts on A in equal size and opposite directions. So the example here is that if you hit a wall with your fist hits the wall. So this is the force of fist on wall. As you interact with the wall, it interacts with you. And so the wall is going to hit your fist with the same size force, but in the opposite direction. Now, obviously, subscripts like wall on fist are not very friendly. So we usually don't do that. But for today, just to make sure that you understand what the interactions look like, I'll use these kind of bigger subscripts. So I went ahead and filled these in just so we didn't take the time together. They're pretty straightforward, and I know you've done some similar stuff already. Feel free to pause it and copy them down, whatever works for you. It's your notes, it's up to you. The one I did want to talk about is number 4, because this is one that folks sometimes struggle with. So just the idea that the moon, although obviously very large, is so much smaller than the Earth that we don't, that, okay, what I'm trying to say is that even though the force of the Earth on the moon towards the center of the Earth, that's just the weight of the moon, that gravitational force. That we have an equal and opposite force on the Earth due to the moon. But we don't see the Earth accelerating as much as we see the moon accelerating, just because the mass of the Earth is so huge compared to the mass of the moon. And so we see the moon changing direction as it travels around the Earth. We'll talk a lot more about that later. Okay, so let's take this Newton's third law idea and apply it to some problem solving. So in this problem, we have an applied force F that's pushing on block 1, and then block 1 is pushing on block 2. So the first thing we are asked to do, our ultimate goal, just so you know, it's not very clear here, our ultimate goal will be to determine how large the force is that M1 exerts on M2. So we're going to go through it very painstakingly first, but then I'll show you some shortcuts that can make this go a lot quicker. Okay, so the first thing we're going to do is look at mass 1 and mass 2, each of them on their own. So for mass 1, we have the gravitational force straight down. And since there's 2 of them in this problem, I'm just going to call it M1G. We have the table pushing up. Again, since there's multiple normal forces here, I'll call that Fn1. Those 2 forces are the same size. We have this applied force F to the right. And then we have block 2, right? So block 2 is like in the way. And so as block 1 tries to move rightward, it experiences a force leftward from block 2. And so the way that I usually would write that is F2 on 1. So that's the force that block 2 exerts on block 1. So those are the 4 forces acting on block 1. Let's try block 2. So go ahead and try it. Maybe pause it, draw it, and then start up again to see if it matches. But here, if you're back, we have M2G straight down. We have Fn2 straight up from the table. And then we have block 1 pushing on block 2. Now the force F that doesn't act on block 2, but the block 1 pushes block 2 to the right with a force that's equal and opposite to the force that block 1, sorry, the force that block 2 exerts on block 1. So this pink arrow will be the force block 1 on block 2. Now, as far as and then we're done with that one. So as far as like what's physically happening for block 1, there is an applied force to the right. And since block 1 pushes on block 2 pushes on block 1. And then block 2 only experiences block 1 pushing it to the right. I don't know if you can hear my dog drinking. It's great. Okay, so now we're going to write the net force equations for the blocks. We're really only going to worry about the x direction here. Technically, of course, there is stuff happening in the y direction as well. We're only going to focus on the x direction, so because that's the acceleration. Okay, so the first equation is always F equals ma. Second equation comes from the diagram. And then it says set them equal, so we'll do that. M1A equals F minus F1 on 2. And then for block 2, we only have one force acting on it. Wasn't that snazzy? That's a new tool I just learned about. Anyway. So the only force causing it to accelerate is the force of 1 on 2. Setting them equal. All right. So our first goal, so we want to oh, you know what? That doesn't look right. This one here, maybe, I'm sure you noticed long ago. This here isn't the force of 1 on 2. This is the force of 2 on 1. They're the same size, but I just want to make sure that my equations match my diagram. Okay, let's move on. So our goal is to find the force of 1 on 2, the force of 2 on 1, that internal interaction, but we don't know the acceleration. And so neither of the equations that we've written will work to solve for the force. So the first thing we have to do is solve for the acceleration. So to do that, there's a couple different ways to communicate this. So this will be method 1. In method 1, we're going to add up the two equations. So let's say this is equation 1 and this is equation 2. So we're going to start by adding the net force equations at 1 and 2 together. And the reason we're going to do that is that will eliminate that internal force. So On the left side, I'm just adding up the MAs. On the right side, I have F minus F2 on 1 plus F1 on 2. But these two forces are the same size. So it's like -3 plus 3 or whatever. So since they're the same size, they're going to cancel out. That's going to be a reality throughout any problem like this. Internal forces cancel out if we're looking at the whole system. And so since our goal is to calculate the acceleration, now I can factor out m1 and m2 and divide both sides by the mass to get a equals F over m. So what we have here, those are arrows. They don't look like them. What we have here is the total force on the system divided by the total mass of the system. So we know those things. Those were given. The force F is 2.5 and the masses are 3 and 2. Part 1 asks us to find the acceleration. So just plugging into the equation that we just found, this is 2.5 newtons over 3 kilograms plus 2 kilograms. 2.5 divided by 5 is 0.5. All right, now we are ready to find the magnitude of the internal force. So now that we know the acceleration, we can plug into equation 1 or equation 2. Since equation 2 is simpler, I'll choose that one. So how I'd say this is we're zooming in. So basically we're going to choose one of the two blocks to focus on in order to calculate the internal force. Okay, so equation 2 says that M2A equals force of 1 on 2. And so that internal force is 1 Newton. Okay. Now, what if in this next part, that same size force F is applied to M1? Sorry, the same size force F is applied to M2 instead of M1. And so that push is just now to the left on the system instead of to the right. So the question is, which would stay the same and which would change? Okay, so I want you to answer that, and then we'll come back. Okay, welcome back. So let's see. So the acceleration would stay the same magnitude, right? Since the equation for Newton's second law is acceleration equals net force over mass. The magnitude of the acceleration would stay the same. The direction would change. What would change though is that internal force would change. Instead of being 1 Newton, it would be larger because now instead of the big block pushing the small block, the roles would be reversed and the small block would push the big block. And so that's going to require a larger force. So the internal force would increase because it now accelerates the larger block with the same acceleration. Okay. Here is an application of this same idea called an Atwood machine. And an Atwood machine was developed in order to determine the acceleration due to gravity. But basically for us, it's just a pulley system. So I'm going to show you an example. So here's a little simulation of an Atwood machine. We see that one mass is larger than the other. If they're the same size and we hit start, nothing's going to happen. The string is going to be massless at this point, and the pulleys are also massless, so they won't affect the situation. But if we nudge mass 1 up a little bit so that now it's heavier and hit start, we'll see the heavier objects start to accelerate downward and the lighter objects start to accelerate upward. However, remember, on a free body diagram, we don't have information about the direction of the motion, just the direction of the acceleration. So we're going to switch back. Whoops. Okay. All right, so first thing, I don't actually know, even though I know the sizes of the masses, I don't know which way this thing is moving. Whoa, why is it so fat? Oh, wrong tool. Okay. But we do know which way they're accelerating. The heavier object's going to accelerate towards the ground. And so we're going to call the direction of the weight force on M2 the positive direction. So this is a little strange. So basically what happens with a Atwood machine is the axis bends and follows the string. And so even though certainly both of these have downward weight forces, they're in a tug of war, right? The two weights aren't working together to accelerate the system, they're working against each other. So what we're normally going to do is call the direction of the weight of the heavier object the positive direction, and the direction of the weight of the lighter object the negative direction. There's a lot going on already over here. That's okay. I'm just going to draw the free body diagrams right below. So okay, so they both experience a downward gravitational force. Where M2G is greater than M1G. And then they also experience a tension force. That's the internal force between them. The tension force, I want you to think about it. Which one? Okay. How does the tension compare to the weight of M2? How does the tension compare to the weight of M1? Well, we know M2 accelerates downward. So that must mean that the tension force on M2 must be less than the weight of that block, because otherwise it would accelerate upward. We also know that M1 accelerates upward. So that must mean that the tension on M1 is greater than its weight. We also know that this is a Newton's third law pair. That tension is essentially the force of 1 on 2 and the force of 2 on 1. And so they're the same size as each other. You'll notice I didn't label them T1 and T2. And so a good thing just to know is that the tension is going to be greater than M1G, but less than M2G. Okay, so now let's dive in. Our goal is to calculate the tension in the cord. And so the first thing we need to do is determine the acceleration. Now in method 1, we wrote the two equations for the system and then added them up. In method, which is honestly probably the best way to approach this, but I'll show you method 2. Method 2 would be to consider the whole system. Okay, so the net force on the system, we're going to start with M2G, and then we're just going to go through the whole situation and just continue to accumulate forces. So the first thing I have is M2G. That's in the positive direction. Then I have the tension pulling up on M2. Then on the other side of the pulley, I have the tension pulling up on M1. Now, even though it's also pulling up, it's pulling in the positive direction because it's working in the direction of the acceleration. But then working against that, I have M1G. And so like we saw earlier, the internal force cancels out. It's not going to affect the overall acceleration. In the denominator, we need the total mass of the system. So that's going to be M1 plus M2. Okay, so now we can plug in. I'm going to factor out that G. And you'll notice I didn't plug in negative 9.8 because G is 9.8. The negative sign, that's out front. That's part of the equation, not part of G. Okay, so now that we have the acceleration, we can zoom in on block 1 or block 2. Since we're looking for the tension, I'm going to zoom in on block 1 because on block 1, the tension's in the positive direction. Okay, so I'm going to zoom in on block one. So I know the net force on block one is M1A. I know the net force on block one is T minus M1G. And factor out that 1.4. All right. So, and this checks out in that we knew that it should be greater than M1G and less than M2G. And M1G is about 14 newtons and M2G is about 29 newtons. So this is between those two. All right. For this next one, we're not going to actually solve, but just set up the net force equations for each of the three. So we're going to start, as it says, with a detailed free body diagram. I'm just going to suggest that you redraw the situation. That's not flat. Over here. With some more space between them. Okay, so we have a gravitational force on each of them. We have a normal force on this guy. And since we have two strings, we have two tensions. And so I'll call the tension in the top string T1 and the tension in the bottom string T2. Now this system is accelerating downward. And so our axis basically goes like this. I was curious what it would do. Not like that. Like this. And so we'll use that dotted line essentially as the axis. Okay, so I want you to try to write your net force equations for each of the, for object A, pause it, and then come back. Okay, so let's see how we did. So let's do block A. Now, strictly speaking, there's also what's happening in the y direction, but there's no acceleration in the y direction for block A, so we're not going to worry about it. They all have the same acceleration, so you'll notice I did not put a subscript on the acceleration. Oh, I should have paused it. Okay, think about what's next. Okay. So for block B, we have its own weight pulling down, we have T2 pulling down, and then we have T1 pulling up. And then finally for block C, we have its own weight pulling down, we have the tension in the rope pulling up. So if our goal was to determine one of those tensions, we would start with either method 1 or method 2, looking at the whole system. So for the system, the only force accelerating it is the weight of block C, because, the weight of blocks C and B, because these two forces don't have anything canceling them out. Like they're an external force on the system from the Earth. But then the two tension forces, those cancel out there, the T2, T1, and these cancel out as well. And so the net force on the system would just be the sum of the weights of B and C, and they accelerate all three masses. All right, almost done. So in these last couple, instead of going through this huge process, we're going to look at proportions and a quick way to do this. So going back to the beginning, not the beginning, number 5, we had a 2.5 Newton force. And after doing all of this work, we realized that the internal force on block 2 was 1 Newton. So one thing I want to point out is that the mass of block 2 at 2 kilograms is 2/5 of the total mass. The total mass was 5 kilograms. M2 is 2/5 of that. Also, the total force was 2.5, and the internal force was 1 Newton. 1 Newton is 2/5 of 2.5. And so the proportion of the force needed to accelerate M2 is equal to the proportion of its mass compared to the whole mass. So let's use that same idea here. So here we have a 36 Newton force accelerating 24 kilograms total. So how my brain processes this, I'm going to say 4 kilograms is 24, 5, 6, 1/6 of 24 kilograms. So that, okay. That's true. However, really what I care about is the 20 kilogram piece of it. So what I care about is what proportion of the total mass is being accelerated by the internal force. So since the mass being accelerated is 5/6 of the total mass, the internal force will be 5/6 of the total force. So that's 5/6 of 36. So this approach only works in multiple choice. If it's a free response, you'd have to give some more justification than this. But in the multiple choice, you want to work as fast as possible. So using that same idea, take a look at 9. So when the frictionless system shown is accelerated by an applied force F, the tension in the string between the blocks is what? Okay, so we're interested in this tension T pulling the 1 kilogram block to the right. Okay, so take a moment, look at the method we used in 8 and pick an answer for 9. And so what I would do is I would say 1 kilogram So since the mass being accelerated by the rope is 1/3 of the total mass, it's going to require 1/3 of the total force. Okay, last one, and number 10, a block of mass 3m. Our goal is to figure out the acceleration of the descending block. Oh, this is actually a little easier. So now we're going back to just acceleration. So only the weight of this little guy is pulling all of it, right? That weight pulls itself, but it also pulls this. And so for the system, the entire weight, the entire force is mg, but the mass is 4m. And so this one would be A. Okay, that was a lot, but I wanted to share it with you, and I'm sorry. I hope you have a good rest of your day.